Thank you so very much, Aaike. Please step forward to be with us here. Aaike van Vugt, VSParticle. You are not only co-founder, but also CEO from VSParticle. Delft-based startup. You were graduated as a chemical engineer.
That's correct.
In 2014. I could ask you the question as well. Could you have imagined that now, 11 years later, you will be standing here with the story you are about to tell us? You founded the company, you have international recognition already, and also very much committed, like Will, your colleague, entrepreneur, to get things done and to really use those new materials to address those challenges in, as said, the energy transition. So, delighted to have you. The floor is completely yours.
Thanks.
Aaike.
Thanks for the nice introduction. Hello, everybody. My talk will be slightly different. I am more of a visionary guy, so you will see that I will speak maybe less about VSP and our business, but more where I believe the high-tech ecosystem in the Netherlands could go to. I think most of you know the great success of ASML and chip manufacturing and how the world is at our knees if it comes to AI chips. But this will not take decades into the future. So what will be the new high-tech ecosystem where we can shine as Netherlands, where we can shine as unique ecosystem? And I would give you my glimpse into that future, where I think we can have this critical asset that everybody relies on. We will not do everything, but what is the most critical assets that we can dominate and how we can stay a very fruitful country? I want to start with the fact that our ability as humans to create new materials and craft them has always led to prosperity in society. Without our ingenuity, without our interest to play around with stuff at the atomic scale, we would not be sitting here today as we are sitting here now. And I do believe that this ability to craft the world around us will also be very important in the futures to come. A bit of perspective. From my perspective, the history of inorganic materials, this is not anything to do with CRISPR-Cas or next-generation DNA synthesis or synthetic biology. We are in the inorganics, the stuff that we extract from the Earth's crust. The first wave in human history was discovering the different elements, eliminating or segregating them and understanding what atoms do we have on this beautiful planet. When we knew them and we were able to structure them in the periodic table of elements as we know today, people started to think, okay, but what happens if I mix 2 of them? Or what happens if I mix 3 of them? So we discovered all kinds of different alloys and things like stainless steel, which we used to build the Eiffel Tower in Paris. The third wave is, okay, but now I can mix them, I can create different material properties. Can I make them smaller and smaller? Because the smaller we can make them, the more efficient components and technology becomes. And of course, it ended up in the current silicon age that we have. And again, without this beautiful beast, I would say, AI would not exist today. And that's something that many people don't realize, how important this high-tech ecosystem we have in the Netherlands is by enabling these machines and then by enabling the advanced AI chips we have today. I think if you look into the next generation AI factories, they are a marvel. Nobody, I think, decades ago could imagine that we could control 20 quadrillion transistors by pumping in gigawatts of energy to just flip enormous amount of bits. So again, the machine of ASML makes these advanced patterns. They go into an NVIDIA chip that already starts to consume watts of energy. Then those chips go into racks. They start to consume megawatts of energy. And then hundreds of those racks go into an AI factory consuming gigawatts of energy. It's a staggering amount. Building 1 gigawatt of AI factory costs 30 billion. 1.5 trillion is currently invested in new facilities, just operating computer chips, just flipping 20 quadrillion transistors on a continuously basis. But what if we could leverage this unique infrastructure we have in the Netherlands, this philosophy of controlling quadrillion transistors continuously, not just to flip bits into zeros and ones, but to flip molecules and fight climate change. Flipping bits has always been built on solid layers, PVD, CVD, ALD. I think many of you know them. But they are always designed to make solid layers because then ASML can do their trick, do lithography and make very fine patterns. But you can't solve climate change with solid layers. There's not enough interaction between the layer, there's not enough surface area between the layer and the world around it to really do something at magnificent scale. We need porous thin films. Thin films, tens, hundreds of nanometers thick with extreme porosity. The more surface area, the better, because the more surface area, the more molecules we can, let's say, change. But making porous thin films is something humans are very poor in. We are using decade-old technology coming from, let's say, coating, wet coating technology, slot die coating, spray coating, inkjet printing, to make a kind of porous structure. But we need these extreme surface areas to make use of green electrons, basic chemical building blocks, water, CO2, N2, and then on the surface of these porous structures, they are interacting with electrons to form new chemical building blocks, green hydrogen, green ammonia, green sustainable aviation fuels. So we are building, or at the moment, we see a new ecosystem being built that is not focusing on flipping bits, but is using the same infrastructure, the same methodology to flip molecules. On the left, you see our beautiful spark ablation. That's where my company, VSParticle, comes in. We have built in the last decade a technology that is fully optimized for printing thin, porous layers. We can print the most extreme porosity in those very thin layers, and therefore, I think we have a good reason to play in this market. We print those structures, and we do that by first converting bulk materials into nanoparticles, and our nanoparticles are 2-3 nanometer in size, and then with a very specific gun, we just stack them on top of each other. So these layers are nothing more than small particles, 2-3 nanometer in size, stacked on top of each other. It's impossible to make more porosity on this Earth conditions. This is how such a layer looks like. It's an iridium. It's completely black because it's nanoporous. That goes into a megawatt scale electrolyzer stack manufactured by Siemens or Bosch or Plug Power or Nel. There are many large players into that market. And then they are multiplied into what we call a hydrogen plant. But in the essence, it's very similar to a data center plant. It's just how can we pump in gigawatts of energy and use that energy effectively to make quadrillion molecules being turned around in a very short timeline. How can we use those green electrons coming from cheap solar and wind to flip molecules to either store enormous amount of energy in hydrogen or make green ammonia to fuel shipping globally in a more sustainable way, or create e-fuels? How can we flip CO2 into a sustainable aviation kerosene form to still use the same infrastructure but then not pollute the global even more? And I think this has been the leading force in the high-tech ecosystem in the past decades, and still is, and will still be in the coming years. But I think this is a unique opportunity where the Netherlands is uniquely positioned from my perspective, also VSP is uniquely positioned to be leading, and especially from my perspective on this part. We know, as nobody else in the world, how to manufacture complex machines to make those very fine structures. Again, our machines are not as complex as the beast of ASML, but I'm quite sure that in the next decades they will become as complex, because the structures we make today will not be sufficient to what people need in the coming decades. So our machines will go into a similar trajectory of becoming more and more complex. We need to start, let's say, fighting the physical laws of nature to crank out even more capacity and flip more molecules. So from my perspective, the third wave has been about flipping bits. The fourth wave that will go into the future is about flipping molecules. And with the help, I want to mention it, with NextGen, it's a large subsidy for our company, we are upscaling our technology by 100x. So our technology fundamentally works by creating electrical sparks, a small plasma, localized plasma, to evaporate the bulk material into these very small 2-3 nanometer particles. And with the help of NextGen, we are generating 100 times more sparks per second, upscaling the technology. And the first large-scale system should be operational early next year. But I do think there's more, where I think the capabilities of AI and the capabilities of flipping bits will start to emerge into a singular approach. So developing new materials is a painful process. It's so complex, there's no computer that can say you this material is what you need if you need these physical properties. So scientists are stuck in this trial and error approach. It's the design, build, test, learn cycle. You design your experiment, you design your material, you think this material will be suited for my next generation battery, my next generation solar cell. Then you build it in the lab, you test it in the lab, and then you learn. And based on that learning, you go into the second iteration. But in this work, it can take up to 100 cycles before you have found your breakthrough material for batteries, for green hydrogen, for new generation satellite communication. And it could take up to 10 years easily. And then you found that material in your lab, and then you still need to scale to mass manufacturing. So on average, if you are lucky, you can introduce a new material in 15 years with more than 100 million of investment needed to go through all those different phases. Because of this problem, we have just scratched the surface. From my perspective, less than 1% of all possible materials that we can generate and develop on Earth have been discovered, mainly because this time-consuming and costly process. So there's 99% more to discover, which I think offers the biggest unexploited space, from my perspective, in human history. So what we are currently doing at VSP with our new advanced material synthesis is mainly tackling this second stage, building. So we help customers, we help top researchers, we help top universities to manufacture those new materials at a fraction of the time it took them today. But when we converge our technology with advanced robotics, you can come to something what they call an automated lab. It's a lab on steroids, where you don't ask human beings to make a material, go into an SEM or characterize the material, but you try to push as many materials through your lab as fast as possible, create as much as possible valuable data, and then apply AI algorithms on top, or train AI algorithms on top of that experimental data to basically crack the fundamental code and really understand how the fundamental physics work. And by doing it, so both currently advancing the synthesis, but secondly, cracking the code of material science, I think you can introduce new materials not in 15 years, but maybe in 1 year. There's no reason, from my perspective, why this difference between, in the semicon market, we can introduce a next generation computer chip in 18 months, roughly, maybe not today anymore, but that's very, very fast. In batteries, it takes more than 15 years to introduce a next generation battery. And the only reason, from my perspective, is poor technology and a non-synchronized ecosystem around it. Fundamentally, we could introduce next-generation batteries within 1 to 2 years if everything is optimized and we leverage the right technology. Since last year, we already started to collaborate together with the AI team of Meta. They are on a mission to build an AI model predicting the best possible electrocatalyst or nanoporous layer for CO2 electrolysis or splitting water into hydrogen and oxygen. And this is a nice movie of our lab-scale printer, where we are printing completely unique materials on the fly. We can, let's say, program our printer. It runs for 40 hours, and then it's able to synthesize automatically, without any human intervention, up to 50 unique materials with very interesting properties on that perspective. The reason that Meta approached us is because there are no large experimental data sets that they can use to train their AI models. So they have been scouting the globe to find the right company that is able to synthesize these new materials in a very rapid, very precise way, and that's why they ended up at VSP. On the other side, we are supporting the great team at Differ in the Netherlands to also start building such an automated lab. Partly to accelerate science, but partly to generate huge amount of valuable data that we can use to train new AI models. And by combining or changing the way we do fundamental science and material discovery, but also enabling a very fast-paced to high-volume manufacturing, I really think we can make this flipping bit or flipping molecules into a reality. And today, as a company, we are in close collaboration with some of the largest tech manufacturers globally that are testing our coatings, and we are in a very good position. So hopefully, in the near future, we can start building also, same as the previous speaker, a new facility in the Netherlands where we manufacture those coatings at very high volumes and ship them around the world. Thank you.
Sure. Wow. Thank you so very much, Aaike. Again, very impressive, insightful presentation. We can all imagine why you gained international recognition already so far. I was wondering, because you really gave us a glimpse of what the future might look like. And that is super exciting. And then I was listening to you and I was thinking, isn't this also attracting young people, young researchers? They say, whoa, this is the path, this is the excitement I want to be part of. Or isn't that the way it works?
No, that's definitely the case. We get emails from, let's say, graduate students from the different universities in the Netherlands quite often, that they really are inspired by what we are trying to build and they really want to put their time and resources in such a purpose. Yeah. It's a different dynamic working at VSP than working at some of the large, let's say, companies we have in the Netherlands.
Don't mention names. Don't mention
names.
No, it's different. It's
both
different.
have pluses and minuses, I would say.
For sure.
But it's definitely something that it's something we need. Yeah. But we don't need, let's say, only students that are inspired and they want to contribute. We also need many more suppliers in the high-tech ecosystem that are really eager to work with us in a more intense way, because we can't do everything by ourselves. Yeah. We fully trust in the model we have here in the Netherlands that collectively we can build amazing things. And that's also why we outsourced all the detailed design and manufacturing supply chain already from the initial days of the company. Yeah. So these beautiful systems are assembled by MTA Mechatronics, one of our largest suppliers at the moment. But we would like to work with many more, especially when we are now moving into high volume manufacturing. Yeah.
Could you give some other examples than you just gave, suppliers you're searching for now actually?
So again, it's a gas phase transport of those inorganic particles. So we do collaborate and are in discussion with Bronkhorst, for example, one of the leading suppliers of let's say, high valuable flow controllers. But yeah, there will be many more components that we need. There are high power electronics in the system to generate these high frequency sparks at kilovolt levels. So there we are still looking for strong partners. Of course, we already know quite a lot of them, but if you don't know us, if you've never spoken to us and you think you can contribute a meaningful contribution, then please approach us. Yeah.
Now, I'm sure that this is a strong reach out and people have heard this carefully. Now, actual times, we have competition, it comes from across the world. And I think if I understood you well, you had Meta, who was also making a tour around the globe to find whatever they needed, and they ended up with you. And now I was just wondering, where is the competition?
So on multiple fronts. So partly one of our largest markets is PEM water electrolysis, which is definitely impacted by the US policies at the moment. But still, I think you see in the latest reports that there's a very solid trend moving forward. The main thing is that there are these very beautiful books written about the earlier days of ASML, and you read there how important the initial support from the Dutch government was in saying, okay, this is what we want in the Netherlands, we invest, Without that, ASML would not exist today. It was a mission impossible without any substantial support from the Dutch government. And that's also what I would like to emphasize in addition, is that I'm telling you this story not just for this event, but I hope that collectively we can make a momentum and we can inform the broader high-tech ecosystem that this possibility is there. But it's only there if collectively we take it. And collectively means that the Dutch government needs to make more bold decisions. If they don't say, this is what we want in the Netherlands, then it will not happen from my perspective.
Okay. Now, we will be meeting the minister later on. So, well, just mentioning.
Let's make a
list.
list.
If you say this, that you say, I would love the Dutch government to make bold decisions in order to have you move forward. Now, what exactly do you say then? What would you like the minister to say?
So I think they can be very essential in helping our progress to building this first factory. Let's say factories in China are not built because they have great offtake agreements and everything is worked out. It's just the government says, we want this in China and we will invest in it. Our, let's say, goal is to get offtake agreements and get this whole factory fully financed. But maybe because the timeline that it takes, we are then slower than any other country. So at some point, our success is dependent about the boldness of, let's say, subsidy providers, government agencies, to say this is what we want. And we will take a bit more risk. We will go a bit beyond, let's say, you have fully secured offtake agreements of the factory. We will not become the next Nordvolt in that perspective. But it's essential that to make this a success, that the government also decides on what they want and that this is something that they want. And I think it's a unique opportunity for the high-tech ecosystem in the Netherlands.
Yeah, wonderful. Great contribution. I thank you
Thank
very
you.
much. Yes, and we will meet later on during the